This is FET203 Computer System. Which of the following is an appropriate explanation of the LRU method that is used as a page replacement algorithm? Is it A, the page has existed for the longest time and is replaced? Is it B, the page that was last referenced is replaced? C, the page that has not been used for the longest time is replaced? Or is it D, the page that was referenced the least number of times is replaced? So, page replacement algorithms are techniques in which the operating system, or the OS, decides which memory pages to swap out. The OS writes to disk when a page of memory needs to be allocated. Paging happens whenever a page fault occurs and a free page cannot be used for allocation. This leads the OS to reason that pages are not available or the free number of pages is lower than the required pages. If all the frames in memory are full, then to place a new page in memory, we need to replace an existing page. There are different page replacement algorithms for this purpose, and we're going to analyze some of them. So below are some of the different page replacement algorithm techniques. So first of all, we've got the FIFO, the first in, first out page replacement. The LRU, the least recently used page replacement. The MRU, the most recently used page replacement. And the optimal page replacement, as well as the counting-based page replacement. Things like the MFU, the most frequently used, where we have to count the number of times a page is used, or the LFU, the least frequently used. In the least recently used, the LRU page replacement algorithm, the assumption is that since not used or referred for the longest period of time, it might not be referred in the near future. Therefore, C is the correct answer to this question. So, when a page fault occurs, the page for reference is loaded into main memory, and the page address table is updated. If the main memory has no free space at the time, a page, i.e. page for replacement, from main memory is selected, and a page out is performed, and then, subsequently, a page in is performed, in order to put the reference page into free space. Let's consider this scenario. If the page capacity of main memory is 4 pages, and the pages are referenced in the following order: 3, 4, 2, 1, 4, 7, 2, 5, 3, 6, 1, 3. How is page in performed with the LRU page replacement algorithm? Applying the LRU algorithm to this problem is fairly straightforward. Simply remove pages that were least recently used. Proceeding this manner leads to the chart shown on the next slide. So here we have our table for page referencing. So here we have the order in which the pages are referenced. Here we have whether we have a main fault, and here we have a table that kind of looks like what our main memory would look like if we performed this set of page referencing. So for the first 4 cases, no matter what we have, we're always going to be using a page in. The reason for this is that there's always going to be at least 4 spaces in memory as per our examples. So first of all, we insert a 3, then we insert a 4, then we insert a 2, then we insert a 1. So we're left with 3, 4, 2, 1 as our input. Next we try and access 4. So here you can see we access our 4, but we've already accessed 4 in the line above, so all we do is rearrange the order in which the pages have been accessed in. Next we access 7, and this creates a page fault because there isn't room in main memory for this page. So what we have to do is remove one from our previous selection. As we're using the LRU, the least recently used algorithm for page removal, we use a page out on our least recently used page. This happens to be 3 in this case, as it was the first page accessed. So we remove the 3, and what you can see here is that the 214 will stay constant, 214, and we will insert our 7 at the front. So this is the kind of algorithm that we're going to perform whenever we have a page fault, i.e. we try and store another page when there is no more room in main memory. So let's go through and see where other page faults occur. When we access the 2 here, as we've already got a 2 in our table, all this does is reorder the main memory, and the recently used 2 will go to the front as it's the most recently used page. Then we try and access 5, and this creates a page fault as we don't have 5 present in our table. So we have to insert 5 at the front and reject the 1 at the back. And here again the 472 stays the same. On the next line we try and access 3, and the 3 is inserted at the front, but the 4 has to be removed from the back. On the next line we access a 6, and there's no 6 in the table, so the 7 has to be removed, and again 253 stays constant. Here we access 1, and again a page fault occurs because we don't have a 1 in our main memory, so 1 is accessed and 2 is removed. So finally we access the number 3. Now when we access the number 3 at the very end here, we already have 3 in our table, so there's no page fault. So all this does is reorder the main memory, and our final output of memory is going to be shown here, which is 5613. So the other choices we had in the example, A was describing a first in, first out page replacement algorithm. B was describing a MRU, or a most recently used page replacement algorithm, and D was describing the least frequently used, or the LFU, page replacement algorithm. So here we can see our answer is C. And what we've analysed here is different types of page replacement algorithms, and also had an in-depth look at the least recently used page replacement algorithm and how memory would look if we performed a page lookup.